Okay, so thanks for the introduction. And I also think it's a very interesting talk, but it's mostly because it's a topic I'm currently enjoying to work on. And yeah, I will talk you a little bit through the kind of issues we are interested in digital twins. Digital twins can be a lot of things, so I will try to clarify a bit to begin with sort of where we are zooming in on the topic. So yeah, so I gave the talk the title Self-Aware Digital Twins, which is really kind of where we are interested in the twin reasoning about its own configuration and trying to adapt what it's doing to changes in the system that is being twinned. So that's kind of the topic we are addressing here. And my plan for the talk now is to first introduce digital twins a little bit and argue why I think they should be self-aware. Then I will talk a bit about how you can program self-aware digital twins so very concretely. Talk a bit about how digital twins can adapt to changes in the twin system, so the system they are mirroring. And I would like to end by discussing a little bit, since we are in a formal methods seminar here, so what does correctness mean in this setting? So we have worked a bit on it. I think there's a lot more to be done. So that's the basic plan. So first of all, what is a digital twin? So I should start by saying, and I think it was mentioned in the introduction, there's a lot of hype about it. They were talking about Industry 4.0, the transition to the next level of digitization in industry and so on. And basically, a digital twin can be seen as a means to understand and control assets. And this is assets in a broad sense. So we can talk about assets in industry, but we can also, and increasingly, think about assets in nature or assets in society. And any company with a minimum of self-respect today has a digital twin and boasts about it on its website. So this is just a fact. And here are a few examples. So for example, General Electric announced how they managed to increase their energy production from wind farms using digital twin technology. We have examples from hospitals, how they reduce delays in operating theaters by introducing digital twins. We have examples from production, for example, the Johan Sverdrup oil field, where they claim that digital twin innovations boosted earnings by 200 million plus in the first year of operation. So we have this kind of success stories going on, and this kind of line of storytelling stems back to the space mission program from NASA. So this is where the notion of digital twin was popularized, and I included here the definition from NASA of a digital twin from their roadmap from 2010, and I bold-faced a little bit of the buzzwords to just give an impression what it's talking about. Integrated multiphysics, multi-scale probabilistic simulation system with the best available physical models, mirror the life of the flying twin, being ultra realistic and so on. And thinking a bit about this and coming from formal methods, it's kind of opposite of everything I believe in about models, because I believe a model should be as abstract as possible, while NASA here wants the model to be as realistic as possible. And that's absolutely not how I'm thinking about models. So I think a model should be as abstract as we can get away with for the kind of properties we're interested in. Now, if we see a more recent definition of a digital twin, here is one from the National Academy of Science, Engineering and Medicine from this year. So it's still a US definition from 2024, and it has changed quite a bit. So here they talk about a digital twin as a set of information constructs that are virtual, that mimic the structure, context, and behavior of a natural, engineered, or social system, or system of systems, is updated dynamically based on data from the twin system, and has predictive capabilities. So I think for me, this is a more interesting, more abstract and high-level definition of a digital twin. So now, what is a digital twin? And this is the way I normally explain digital twins. So let's assume we have some system we are interested in twinning. So here's a physical system, and we're going to make a twin of this system. So let's assume we have a model of this system. So now we have the physical system and we have the model of the system. But the digital twin should be a live replica. So let's add a stream of observations. Let's assume we can equip this physical system with sensors, for example. So we have streams of information going from the physical system to the model and integrated in the model. And this is popularly called the shadow. So it's a digital shadow. It's shadowing the real system, and it's kept in sync via this link of this continuous flow of data from the physical system to the shadow. Now we can add an action space. So the twin or the model over here can now also start performing actions that could influence the behavior of the physical system. So we have a kind of feedback loop going on. And this is typically the way we think about the digital twins. So now we have this terminology of the physical twin and the digital twin, and they are kind of in sync in the sense that observations are all the time flowing from the physical twin and keeping the models in the digital twin up to date. Now it's also more than a model in the sense that it has this tight connection to the physical twin, but it's also more than a control system in the sense that there is a model. So it's a kind of model-based control, if you like. Now, an interesting consequence of the fact that the digital twin is a model and not just a control system is that we can use it to explore decision space for the physical twin. So it's not just, or not necessarily just about fine-tuning some parameter on a physical system. It could be much more explorative and have much more interesting predictive capabilities, to refer back to this definition. And also one interesting aspect of this is that the lifespan of the digital twin and the lifespan of the physical twin may be very different. And if you think in terms of engineering, the digital twin might exist before the physical twin, and it might also exist when the physical twin is no longer. If we think about natural systems, it would obviously be the other way around, that the physical twin is out there and the digital twin will be alive for some shorter period of time. So what does it mean to be a live replica? And if you think in terms of engineering, there's a notion of a digital thread, which is tightly coupled with digital twins, which is about how to organize the sort of the lifetime of design documents, requirements, software that all go into the system that will be represented by the twin. So we can think about this as a kind of, in an engineering terms, about life cycle stages. We have this design time, we have development or construction time, we have operational time, and we even have decommissioning at the end. And we want the digital twin to sort of transition from one stage in the life cycle of this system to the next. So we want the twin to evolve in tandem with this system that is sort of gradually moving from one way of functioning, one way of operating to the next. Today, this is an enormous business management problem. So there are these stacks of documents that need to be organized. And there's a big push now in industry to move into a digital world where this information is digitalized and related to each other. So this process of digitalization turns this business management problem into a software engineering problem. But we talked about not only engineering systems, but also natural systems or social systems. So do we have similar kind of life cycle perspectives on a natural system? So since I'm from Norway, I tend to think in terms of fjords. So we could think about a fjord and what would be a kind of transition from one life cycle stage to the next for the fjord system. And there are various examples we could think about. We could think about disasters like a tsunami or something which radically changes the ecosystem in the fjord, or some major pollution spill of some kind, or even in the Oslo fjord, which is close to Oslo, we have the problem of alien species invasion. So we have, for example, now aggressive oysters coming in the fjord, and we can think about this as a change which is sort of radically affecting the ecosystems. So the way that industry is now trying to address this problem of the digital thread is in terms of asset models. So they are creating models to construct and relate all these documents. And here's an example from an EU project called READY, where we see we are trying to digitalize and relate the requirement stage, engineering stage, to turn this into design model, which is then going into fabrication and finally into operation. So we have this kind of digital thread where digitalized documents are sort of passed on and reorganized from one stage in the system to the next. So this is a little bit of background. So now, how can we think about these digital twins? And the way I'm thinking about it is in terms of layers of information. So at the bottom here, we have a data layer, which consists of domain models, observations about the physical system, parameter spaces for models, and so on. And then we have an information layer, which is based on organizing this data. So then this idea about asset models and turning this digital thread into organized information lives in this layer of information here. And on top of this, we have an insight layer, which is about creating insights into this structure. And this is typically now in state of practice. It's about dashboards, visualization of things, and that kind of stuff. What kind of insights could we talk about? Well, typically we can distinguish different kinds of insights. So we have descriptive insights, which is about providing explanations of some event that has happened. So what happened and led to this event? We have predictive insights, which is about understanding the near future. So what may happen in the near future? Then we have prescriptive insights, which is to set up this twin in order to provide advice on different possible outcomes. So this is sometimes called what-if scenarios and the analysis of what-if scenarios. And then we have this reactive layer where the twin itself can go in and make decisions about the physical system. So this is typically related to automated decision making. And so the way I'm thinking about these twins is in terms of how these two top layers are talking to each other. So I'm going to talk about the structural twin, which is the organized information layer, and the behavioral twin, which is about simulations or analyzing the behavior of the system. So that's all good. And we have now heard this story about sort of model-centric software. So we have software which is sort of organized around models. So the model is at the center of the software. And we are moving from business problems to software engineering problems. We're moving from software engineering problems to problems about how these models interact with knowledge graphs or organized information. And we are turning from general software to the problem of how to manage models. So how to compose them, how to configure them as we are moving in this life cycle of the physical system that we are twinning. And now the question is, how can we program a system like this? This is a problem we are trying to address and we are exploring, and I will not say we have the final word on the matter, but I'll tell you where we are. So our approach to this problem is based on reflection. And now maybe some of you are familiar with reflective programming, but if not, believe me that it can be a bit tricky. What is reflection? Well, it's the ability of a process to examine, introspect, and modify its own structure and behavior. And in particular, we are interested in reflection, so how the digital twin can examine its configuration and behavior and modify it with respect to external reference points. And the reference points we are interested in, I mentioned already, so we have observations from the physical twin. We have these life cycle stages that are moving around, so there are these various triggers that should change the behavior in the twin. So now the question is if we can use reflection to address this kind of evolution. The digital twin needs to evolve in tandem with the physical twin. The reflection is a tricky programming activity. We have these reference points, this digital thread, this history of development, these life cycles, and so on. And then we have the domain knowledge. We have the sensor data coming in, the expert's understanding of how the physical system must behave, and so on, that we can try to exploit in order to adapt the digital twin to what is going on in the physical system. I should mention also at this point that what we are doing now is very related to this concept of models at runtime, where the software is maintaining a model and using this model to make decisions. And this model that we are going to work with, it has several components. We have the domain model, which we can think about as the variability space of the physical system. We have the asset model, which we can think about is how the physical system is composed right now. Then we have the domain of analysis, which is really the variability space of how we want to configure our digital twin. For example, we would want to configure it differently for different kinds of analysis, like predictive or prescriptive and so on. And then we have the twin model, which is really the twin equivalent of the physical systems asset model. So it is describing the current configuration of the digital twin. And these are the kind of components that we are now going to be playing with in our reflective programming. So here's an example. So let's assume that we have a house with some rooms, and in each room there's a heater, and we want to maintain some temperature in this house. Now we can use a digital twin for this purpose, and that would mean that we basically develop this structure layer and the behavioral layer. And the structure layer, it will have domain knowledge about houses. So what are houses? What are rooms? How are rooms connected? What kind of simulator should we use for different rooms and so on? And then we have the asset model, which describes this specific house. So here we are seeing a house with 2 rooms. So there's one inner wall, there's one heater in each room, there's an outer wall on each side and so on. And then we have a behavioral twin, and this behavioral twin will then integrate observations. So for example, temperature readings from the house, monitors that monitor the configuration of the twin, and it will also orchestrate simulators. So we are going to use simulators to control the temperature settings of these heaters. So the twin configuration now consists of a number of simulators corresponding to the different parts of this asset. But then in addition, there's the domain of analysis, which tells us what are the possible ways we could configure the behavioral twin. And then we have the twin model, which is now in the structural layer, the description of how the behavioral twin is currently instantiated. So what we did was to address this problem by introducing a small formally defined programming language that we called small. And small is really a kind of application-specific or domain-specific language which is customized for programming twins, which has this structure of a behavioral and a structural layer. So what is small? It's a small object-oriented programming system that supports reflection into knowledge graphs. And what does it mean? It means that a runtime state in small is automatically lifted into this structural layer and integrated with domain knowledge formalized using ontologies. And that means that we can now use reasoners about ontologies to ask questions in this knowledge base, which includes the representation of the runtime state of the program. And in particular, small programs are reflective in the sense that programs can use these reasoners themselves to query the knowledge base about themselves. In addition, for the behavioral layer of the twins, small can encapsulate simulators using the FME standard. And that means that specifically we can use this semantic reflection in small to automatically represent the configuration of these simulators as part of the structural layer. A bit more in detail. So these simulators now, they are really embedded as objects in small, and objects can be created dynamically. And this is also now supported for these simulation models, which means that we can boot up instances of simulation models that are encapsulated behind objects in the language. And these could be black box simulators of various kinds, but they could also be other kinds of models that we want to integrate into our analysis system. And FMI, functional mockup interface, is an industry standard for interfacing to simulators, but it can also be used to interface to other kinds of modules, sensors, for example. But this gives us a way now of dynamically embedding different kinds of models as small objects into this runtime configuration of the digital twin. So here's a small example. So we have this class of rooms that we saw before. And basically now we can now boot up a simulator for a particular room by providing a path, providing some initial parameters. We are encapsulating it in an interface for functional mockup objects. And then we are embedding this object into an object which is representing a room in our system. And we can now talk to this object as we would for the simulators. We could ask it to advance time. We could give it input and get output variables and so on. So this is a very simple way that we boot up simulators inside Smol. So now we have this system where we have these shadow objects that are simulating behavior in the different rooms. They are connecting to each other, exchanging values. And then we have the real house where we can use the same kind of objects to embed sensor data, for example, temperature readings from the different rooms. And now we are interested in whether the shadow system can control this or can replicate the temperature development in the rooms. And this we can simply now do by connecting the values that we are reading from the smart house with the values that we are reading from the simulator, and we can monitor the difference between these. So this is basic setup for a small digital twin. We have functional mockup objects as wrappers for system observations. We have functional mockup objects as wrappers for the behavioral twin, and we can monitor the drift between model and system. And that means that we can now, in this monitor, we can now check whether the difference between what the system is saying the temperature should be and what the model says, if this difference is too big, and then we can basically then do a kind of model repair. So we can try to look for a better shadow than the one we currently have. And there are many possible strategies for this process of finding a better model. We can start exploring parameter values. We can change from one simulation unit to a different one for a particular room, or we can even do portfolio to look over time to see which settings work best. So there are many different options here. But the point is really that there is a configuration space, and we need to organize this space so that we can make decisions about it. Okay, so we have these runtime states, and I showed you how we could monitor these models and compare the values in the models with the values of the real system, but it doesn't tell us how we can organize the configuration space of the twin. So what we're going to do instead is that we're going to connect these runtime states to a knowledge graph. And the basic idea now is that we basically take the whole runtime state and we lift it into a knowledge graph, such that we can use inference systems over ontologies to reason about what's going on in the runtime state. And the way we are going to do this is that we have the ontology of Smol, which is really defining the structure or the vocabulary for the different ingredients in the runtime state. So we have things like process and heap and so on. And then we have the formalization of the program that we are running. So we are also lifting the class definitions and the class table into the knowledge graph. And then we have the actual runtime state. So we are lifting the configuration of object instances, the heap. We can also lift the stack. We are currently not doing that anymore, but it can be done depending on our needs. And then in addition, we can now we can add a domain ontology. So for example, if we are twinning a particular kind of machine, we might be interested in adding to our knowledge graph domain terminology about this machine, which would allow an engineer to understand what's going on and connect this terminology to what's going on in the small program. And we are doing this process we call semantic lifting, which is the implementation or realization of how all this is integrated. And the small ontology is given once and for all, and similar as the domain ontology, so these are simply loaded as files, while the heap and the class table, we are virtualizing them, which means that the knowledge graph here is loaded on demand. So if we ask a query where we need to consult the heap, we will load the relevant part of the heap. And what we are interested in now is to ensure that we can start interacting with this knowledge base in a safe way. So here's an example of how such a structure works. Here we have the twin system, the smart house, for example, and over here we have the shadow. So the small simulation here is a class which is embedding these simulators. So this one in particular will be embedding the sensors for the temperature of the rooms, and this one over here will be embedding the model of the room. And then we can connect these, so we have a monitor connecting them. We can start comparing values from the two sides and so on. So we have this kind of structure that we can explore, and we can use to ask questions about the configuration of the system. Now these FMOs, they are black boxes for us, so we don't know how they are implemented, and we don't know how to represent them or their implementation in the knowledge graph. So we are simply here lifting a model descriptor, so an explanation of what kind of model it is. We are lifting its path, so we know where to retrieve it. And we are lifting the buffer, so basically the input-output value. So we can at any time see which data is being exchanged with this black box without actually knowing what it is doing inside. So here's an example of how this kind of semantic programming can work. So let's now assume that we have a building which consists of a list of these rooms that we have seen before. And these buildings are organized in streets, and we have now an inspector who wants to do some inspection on a certain set of buildings. And which buildings do we want to inspect? Well, we are going to want to inspect buildings of the category villa. Now, villa is not defined in the small program at all. So villa is a concept which belongs in the domain. And in the knowledge graph, we are simply going to say a villa is equivalent to a house with a certain amount of rooms. So the list of rooms is, let's say, smaller or equal to 3. So we can use this query now in the runtime program to get a list of all the relevant buildings that are classified as villas in the domain. So this is an example of how this works. And this means that now the buildings that we have in the small program will be lifted, and the knowledge graph will recognize which ones are villas based on the rooms or the length of the list of rooms, and return those buildings back to us. So what we have now is we have this semantic reflection, so we can lift our runtime state up to the layer of the knowledge graph, and we can ask questions about the runtime state. And we saw also that we could add these additional definitions about the runtime state. So about our buildings have these rooms, but we can also, and this is what we specifically want to do, we want to link this graph that we are lifting to a graph of an external asset model. So the description of the physical system as they were developing, as I mentioned in the beginning, in engineering, for example. So the way we want to do it now is that here we have our small program, so the twin configuration, and we have the lifting and the reflection, which is going on here. We can ask the runtime state is lifted into a graph, and we can query this graph, so we are reflecting back into the system. But what we want to do now is to connect this graph with a graph which is explaining the domain, so this life cycle engineering picture that we saw in the beginning, such that we can relate objects in our runtime state to information in the domain. And in the same way, we would like to ask the twin questions in the language of the domain which results in an encoding on the program side of the kind of analysis problem that we are interested in. So this is the basic setup now, that we use small with its external simulators. So this configuration of orchestrated simulators to capture the effects of some process. But we want to interpret the states of this program via the ontology to really interpret it in terms of domain knowledge. So how does this work? So how can we express what the small runtime object represents in the domain? So how can we help this lifting into the semantic layer? And the way we're doing it is as follows. So if we have an instance of some class C, it will be lifted into an object. This is a runtime value. It's an object in the runtime, and it is related. So it is an instance of a program. So this is in the program, and this is in the runtime, and we have this relation between object and class. But now we are in the semantic layer, so in the knowledge graph, and not in the runtime system. Now let's assume that this object has some field f with some value n. Then this will be lifted in the same way. So in the knowledge graph, this runtime object will have a relation, an f relation, so f is now declared in the program, so it's a program information to a specific value n. But now we want to connect this runtime object to domain information. So let's say we want to tell our knowledge graph that this runtime object is really representing some instance of a domain concept D. So here we are moving from a class C to some domain concept D. And the way we do it is to say that we want to link this object to some individual of this concept. So here we have a class in the domain, an object in the domain. Here we have an object in the program. Here we have a class in the program. Here we have a class or concept in the domain. So this domain object is an instance of the domain concept. The runtime object is an instance of the class. And we add this explicit models link, which is linking the runtime object to the corresponding instance in the knowledge graph. So now this is done. So this is done by an annotation in the program, which tells us that instances of class C should be linked to individuals of domain concept D. But we can now start playing with how we actually do this linking. So I showed you how a field is lifted into a relation between the runtime object and the value. But we can also tell now the runtime system of small that another field here should have an interpretation in the domain. So here we are telling the small semantic reflection that this field G, we're actually not interested in it as a runtime value, but we are interested in it as a value of the domain object. So this particular domain object that we are linking to should have a field G with value M. And now we can stack these together, right? So we now have the runtime object, we have the domain individual. The runtime object is of class C, the domain individual is of concept D in the domain. And in addition, we have told the knowledge graph that this individual in the domain has a value M according to this relation G. So we are sort of now building a increasingly more complex graph. We can also feed in values from the state in the following way. So let's say we are not interested in lifting this field F from the runtime object, so we want to hide it. And instead we want to tell small that actually this field F should be interpreted as a G relation in the domain. So here we're actually linking the runtime object to its corresponding individual in the domain and telling small that the domain relation G should be given the value in the current runtime state of F. So we can start playing with these things. And in particular, what I find interesting in this line of work is to look at this modeling bridge linking the runtime graph to the domain graph. as a very dynamic entity. So here's an example where we basically decide how the linking should be based on the state of the object. So here we have the example that we can think about this as a guarded expression. So the modeling bridge says that if the value of field f in the object is larger than 0, then we should link it with this g relation to the value of f. And if this is not the case, so the default case will be that we link the runtime object to an individual of the domain concept D. So this is how this structure would look if the field f in this current runtime state has value 1. If it is value 0, this one will not fire, and we will go to the default and we will connect to the domain concept D. So let's go back to our house twinning example. So we have now this house. We saw we have the 2 rooms. We have simulators for the rooms which simulate the heaters in the rooms. We have the inner wall exchanging temperature between the rooms. And we have outer walls where temperature is leaking out, heating the environment, as we say. And now we have this virtual controller. So the twin, in addition, has this controller adjusting the temperatures of the 2 heaters. So now the asset model will specify that we have 2 rooms. They are connected via an inner wall. The left room is related to an outer wall here, the right room to an outer wall there. And it will also tell us which simulators to use for the different entities in the asset, so for the walls and for the rooms. And we add this virtual controller to adjust heaters. And now what does it mean for this structure to be correct? Well, the way we are seeing it is that it's correct if the simulators are configured in a way that mimics the structure of the physical asset. So we want the digital twin now to have a simulator for this room, connected to a simulator for the inner wall, which is again connected to a simulator for the other room, connected to a simulator for the outer wall, and so on, in such a way that we can try to adjust parameters to capture the exact behavior of the house. But now we were talking about life cycle, so how things are evolving. So let's assume now that this is my lab and I get a huge EU project, so I need to employ a lot of new people. So basically, I'm going to add new offices to my lab, and I want to reconfigure the twin to deal with how my office space is developing. So here we have the old office space, and now I'm going to add the lab here and the lab here. So we now have 4 offices. They will be connected. So the old outer wall here is now an inner wall. The old outer wall there has become an inner wall, and so on. And the controllers I have can only regulate the temperature in 2 rooms. So I had 1 controller for these rooms. Now I want 1 controller here and another controller there. So what I want now is the digital twin to detect this change in the asset that is being twinned and reconfigure to adapt to the new asset. And the basic idea we are now pursuing is to use the structural layer, so the knowledge graph, to detect that there's a drift between the structure of the physical system, which now looks like this, and the structure of the twin, which looks like this. So that's the basic idea. So we are assuming that this asset model is kept up to date, for example, by the construction engineers or by sensors or other ways of keeping it up to date. And we are seeing this as a ground truth that we want to connect with the behavioral layer. So this is how it looks. We have the asset model which provides access to the sensor readings, as we saw. We have the asset model which provides access to the structure of the physical twin. And we have the small program that can simulate using various models the different parts of the physical twin. And this is the picture, right? We have the physical twin, we have the asset model reflecting the physical twin, and we have the digital twin over here. So how do we now connect all the pieces? So we want to compare the simulations to the sensor data that we saw we could do using a monitor. We want to compare the digital structure, the structure of this guy over here with the physical structure of this guy over there. And then we want to use self-adaptation techniques to reconfigure this digital twin when the physical twin has changed. So what does it mean that the digital twin is consistent with the physical twin? We're going now to formalize this concept of consistency. And the basic idea now is that we are using this reflection, so the reflection of the runtime state here, to lift the structure of the digital twin in such a way that we can start comparing how these things are composed and try to, and then once we have compared them, we can use repair techniques to reconfigure the digital twin so that it again reflects the physical twin. So that's the basic idea. Now, what does it mean for us to be consistent? It means that the digital twin has the correct structure to operate on the current state of the physical twin. So if the physical twin has changed, the digital twin needs to reconfigure so that it again mirrors the physical twin. And the digital twin should also then use the correct models, correct configuration of the models, and also monitor the correct requirements. So I'm going to show you examples later of how in this life cycle evolution requirements are also typically going to change. So how do we now formalize this in terms of reflection? So we want to have a consistency, we want to have correct requirements, and so on. So the way we're going to approach this problem is to assume that the correct structure satisfies a certain number of constraints, and for each of these constraints, we can ask a question to the knowledge graph. And we're going to call these defect queries. So the idea of a defect query is to ask a question about the violation of a constraint in such a way that the knowledge graph will provide a witness for this violation. And the witness gives us an operational way of doing model repair. And now the digital twin is considered consistent if all these defect queries return empty sets of witnesses, so there are no witnesses to any defect. And here's an example of how this could look. So we have these rooms that we have seen from the smart house. And an assertion about the room is a triple where we have a room and we have a reference to its left wall and a reference to its right wall. So now we can ask in small, we can ask the knowledge base to give us back. So we are asking for the rooms or the triples here, where the room is a room in the asset. And it is linked now via an asset right. So it has a pointer asset right to an ID wall right, and a pointer via the asset left relation to an ID wall left. So that we are going to return this triple for those triples where we do not have a corresponding room in the program space. So we have the space of the domain, the asset here, and we have the program here, and we are going to filter away all the rooms which we already know about. So this is the kind of defect queries that we can work with. Now we are getting a room here. We will have a room which is not in the current configuration of the digital twin, which means we need to now check what kind of room it is, what kind of simulator it should use, and where it should be inserted into the structure. And for the example we have, there are three different possibilities. We have rooms to the left of the old house, we have rooms to the right of the old house, or we can have a room on either side. So the current simulators we're using in this example will only work if we add two rooms at a time. And these are the three configurations. So now we can reconfigure the behavioral twin by creating new simulation elements, inserting them into the structure. We repair the virtual elements that are not reflected in the asset. And then we can check the result by again using reflection over the runtime state to check that now all the defect queries return empty sets. So this is typical way we can do self-repair in this technique. But we can also generalize it a bit more. So we have now seen that we can now lift this digital twin software layer and use defect queries to find out when it is out of sync with the physical twin. But we can also now organize this relation between digital twin and digital thread, which means this evolution of life cycle in a different way. So what we have been looking at is how we can use self-adaptation techniques to organize this space of reconfiguration. And in particular, we are working with this MAPE-K architecture that might be familiar to some of you, which is a reference architecture for self-adaptation, where the idea is that we split the system into a managed layer and a managing layer. And then the managing layer will have a monitor, which is monitoring what's going on in the managed system, an analysis component, which looks for defects, a planning component, which decides how to repair, and then an execute component, which is doing the actual reconfiguration. So how does this MAPE-K loop now look in our setup for digital twins? So this is the setup we had. We had the physical system here with sensor data going to the digital twin, and then actions or commands going back. And when we have seen that we want to have a structural preservation between the two, so we want the structures to be coherent. And we have this evolution over time, so this guy changes, and we need to adapt the digital twin to reflect the new configuration in the physical twin. So now what we're going to do is we are going to reorganize this picture. So we have the monitors from the physical twin to the digital twin, and we have the control and the actions that allow us to adapt the behavior down again. So now we're going to split it in the following way. So the managed system for us now is the behavioral physical twin, and the digital twin will now have a monitoring component, an analysis component, a planner, and an executor, which is basically just structuring the different actions that are needed in order to adapt the physical system. So now here's an example. So let's say that we have these life cycle stages. So one example could be that we have a component which is fully functional and one which is defect. And if we are now we are working with natural systems, so for example basil plants, then in addition to this healthy versus sick plant, we have the different life cycle steps going from a seedling to a sort of a robust plant to a flowering plant. So we have different stages, and we have various of these life cycles going on. And now each life cycle stage will require a different setup, so different components. The requirements, for example, for how much water the plant needs will be different in these different stages, and also different depending on whether it's healthy or sick. So we have a lot of things going on with respect to the digital twin. It is like, what are the requirements that we want to maintain? What is the watering policy? So the controller part and so on. And if we now have many of these life cycle stages, or many of these life cycles with different stages, we basically get a cross product, right? We can have a happy or healthy seedling. We can have an unhappy or sick robust plant, meaning not a seedling, and so on. So we have this cross combination. And the question now is whether we actually want to model this whole complex transition system to mimic all these different life cycle stages that can happen to different or even to the same components in the physical system. So what we're going to do is that we're going to exploit the knowledge graph for this purpose. So instead of describing or formalizing the transitions in this complex transition system, we are basically going to take a completely declarative approach to these life cycles, which means that we don't try to describe, maybe we don't even know why the plant suddenly gets sick, but we try to describe what it means for the plant to be sick, or what it means for the plant to be healthy, or what it means for the plant to be a seedling. So we try to describe what it means to be in a particular stage, rather than how we get to a particular stage. But that means that now when the plant changes from seedling to robust, or from healthy to sick, we're going to need to reconfigure not the managed system, the physical twin itself, but the managing system. So we're going to reconfigure the requirements we use to analyze the physical system, and also reconfigure how we deal with them. So how the frequency of watering, the targeted temperature in the greenhouse and so on, which means that we are now adding a second layer of self-adaptation. This is the layer of the digital twin controlling the physical system, and this is the layer of the self-adaptation of the digital twin to deal with the life cycle changes in the physical system. So the life cycle stages are now a second layer of self-adaptation, and the monitors here are monitoring the structure of the first layer of the twin, but also monitoring the physical system. So we have a feed of data coming from the physical system into this level 2 self-adaptation layer, but also information about the configuration of the twin itself. And the way we are modeling this now is by basically 2 predicates. One we call a membership predicate, which is formalization at the level of the knowledge graph of what it means for an asset to be in a particular stage of a life cycle. And we have a consistency predicate, which basically states what are the components in the managing system that should be considered when the physical system is when this asset is in this particular stage. So these are the 2 predicates that we are working with. And we are saying that different life cycle stages are compatible if one stage may restrict the consistency of another one, but it should still have a solution. And this is something we can actually check by using the knowledge graph. So we can check that these solutions exist. But this allows us now to use repair techniques, so abduction, if you like, over the knowledge graph to look for which components we need at the level of the digital twin in order to make the digital twin consistent with the physical twin for the detected life cycle stages of the different components down here. So we are basically now using abduction. And what does it mean? It means that we look for what are components we could add here that would make the digital twin consistent with the physical twin. This is the question we ask, and we use the knowledge graph to answer this question for us. Okay, so now I have told you about how we are seeing digital twins as self-adaptive systems and how we are using reflection to give them twins this kind of notion of self-awareness to realize what is wrong or what it needs to repair in order to, again, twin the physical system correctly. So now I'm interested in discussing at the end of my talk a little bit what does it mean for this kind of twin to be correct. And what I'm arguing actually is that correctness for a digital twin is about its ability to adapt to changes in the physical twin, including changing the requirements to the physical twin, so the correctness criteria for the physical twin itself. And we have seen some examples of this kind of problems. So do we have the correct requirements for an asset in the physical system at the current life cycle stage? Do we have the correct control policy at the current life cycle stage? Do the different life cycle stages always result in valid configurations, or is it possible to have a physical system in a combination of life cycle stages for which there is no twin solution? So these are the kind of correctness properties we are interested in. In addition, we have correctness for the small language, so for the semantic reflection itself. And here we can talk about, for example, typing properties. So do queries from a program respect the object-oriented model of small, which means are we guaranteed that we get answers from a query to the knowledge graph that we are able to interpret in the runtime state? Or could we get values back that we don't know how to represent at runtime? Another question is whether how robust we are for this knowledge graphs. So could there be bugs which are basically introduced in the knowledge graph and that will then propagate into the digital twin? So these are 2 examples of things we have been working on, which I will now tell a little bit about at the end. So we have seen that we can use various kinds of inductive reasoning techniques or inferences over the knowledge graph to ask questions about the digital twin. So for example, if we have a simulator or an FMO, which is named shadow, and this is of this particular class, if it is linked by a particular relation, if all monitors are linked to a sensor and which is to a sensor which is called shadow. If all monitor instances are loaded correctly and so on, we have the defect queries we have seen before. But what about this semantic reflection itself? So we have this paradox in a way that small is a statically typed language, but the query language is untyped. So we can ask the question, given a knowledge graph, is it possible to guarantee that the execution in small will be well typed, so that we have this standard subject reduction properties for the programming language? And this really amounts to this kind of question. So we want to access a knowledge graph via a query, and we want to assign the result of this query to a list of, so we have a list of class C. And can we now guarantee that every result we get from this query will be an instance of C? And this really amounts to asking whether all the answers to this query are members of the class C in the representation of the knowledge graph. And this we can ask in the following sense. So members we can actually represent as a query, which is give us all the individuals of this concept of being a class C in the program. The problem is that there are no efficient solutions to ask if this query is subsumed by that query. So here we have a problem of query subsumption or query containment, which is really our subtype relation, but we don't have efficient algorithms for it. But what we do have is an algorithm for deciding if the instances of a particular concept is a subset of the instances of a different concept. So what we are doing instead is that we are constructing or approximating the possible answers to Q as a set of individuals, and we check if this set of individuals is contained in the set of individuals of the concept of being in class C in the program. And this is something where we have an efficient mechanism in the domain, in the description logic system, that we can actually ask this question without having any instances at all. And the actual query that we have is a little bit more complex because we can feed values from the runtime state into the query. But the basic idea here again is that we are approximating a set of instances in the domain, and we show that this set is subsumed by the instances that we can understand in the program. And so this is one aspect where we are working now on guaranteeing that these programs are type safe and that we will always understand the results from the domain that we are querying. The second one is about the knowledge graphs themselves. So let's say we want to test if a knowledge graph integrates well with some application. So we have some domain knowledge, we have a graph, and we want to basically test it with our small digital twin. How do we go about it? Do we do unit testing or integration testing? What is the test oracle in this setting? And what we did was to look at mutation techniques. So we basically looked at how to mutate the knowledge graph in such a way that we can discover errors in the assumption that the program might have about the knowledge graph. So that this assumption is typically given by the possible queries that the program can make to the knowledge graph. And of course, it's easy to mutate single triples in this graph, but these are pretty uninteresting in terms of testing, because either they obviously break the system or they have little effect. So what we are doing is that we are mutating larger subgraphs. So we have the domain-specific mutations that change bigger parts of the knowledge graph. So here we have the original knowledge graph. Here we have a mutant generator. And then we get the possible new knowledge graph. And there will be a lot of nonsense knowledge graphs here. So what we do is that we added what we call a robustness mask. And we want to check that the candidate mutant is compliant with this robustness mask. And if it's not compliant, we reject it, and otherwise we actually test it. And in this way, we can gradually develop this knowledge graph, which is really the contract between the program and and the knowledge graph. So this robustness mask, we can gradually add to it as we are developing the mutation test system until we have a clear contract what the program is expecting from the knowledge graph. And here's an example of the kind of problems we found. So we were looking at the twin controlling an underwater robot, and this robot is inspecting a pipeline. And we found out by mutation testing that there are certain structures of pipeline, branching structures, for example, which this robot was not able to handle. So this is a kind of very simple example of the kind of errors we could detect based on this, that when the control program, the twin, was developed, they were assuming certain structures about the pipelines, which need not be the case in reality. And now I wanted to end by just telling you, I've told you a lot about theory now. So how does this look in practice? So here's an example we have developed in small. So here we have the components of a greenhouse. We have a small greenhouse. This is in the Formal Methods lab in Oslo. We have various sensors, and we have various actuators. So here we have like watering pumps. Here we have like humidity sensors. We have the greenhouse. And we are basically constructing the greenhouse like this. So we have a reservoir of water. We have pumps. We have sensors. And we have a small digital twin controlling how much heat and water and so on we should inject into this greenhouse. And this is how it looks. So we have several shelves. We have the plants. So I'm using basils in case my students forget to water them. We have the water tank down here. So this is the schema. The physical twin consists of the greenhouse, sensors, and actuators. The digital twin consists of the software architecture that is realizing behavioral self-adaptation and architectural self-adaptation. The simulation model in this case is simply programmed in small. The driver, which is sort of iterating over the self-adaptation loop, is programmed in small. And the knowledge graph, to begin with, is really a formal description of the system over here. And then we are using time series database to interface the small program with sensors. Now we can have this kind of behavioral self-adaptation. So we want to adjust controllers of water pumps to reach a particular goal, so a requirement in the knowledge graph about how a plant should be watered, what is the desired humidity level in the pot. But we can also adapt or apply this architectural self-adaptation. So we can detect that the basil is sick and then change how we are dealing with it. Sorry, this was the wrong way. And this is how we are doing this. So we add a sensor to the greenhouse, which is an infrared camera. And then we use an analysis technique to look at the chlorophyll production of the plant to detect whether it is producing a reasonable amount of chlorophyll. And then we use this to decide whether it's healthy or sick. And then we use defect queries now to the knowledge graph to detect whether in the greenhouse these basils that we are modeling are compliant with the basils in the greenhouse. So this was just to show you a little bit how this works in practice. This is a software system that you can download if anyone wants to try it and see how this is actually implemented in practice. This is openly available, including time series data for the different sensors in case you don't want to build your own greenhouse. But I would recommend everyone to have greenhouse with basil. So to summarize, so I made a small Venn diagram to show you kind of how this picture looks. So for me, a digital twin is a kind of sweet spot between model-based analysis, configurability of models, and prediction, so ability to do predictions. I think actually, I think a lot of programs in the future might be built in this way of sort of having a piece of software manipulating a model in the middle. There's a lot of industry interest in this kind of systems at the moment. They are interesting in the sense that they are often dealing with cyber-physical systems in the large, so not just like a single controller, but a big factory, for example. There's a lot of interesting analysis techniques to explore. I've just mentioned them. I've not shown you in detail how they could look. And the state of practice today is not very advanced, which means there's a lot of ad hoc solutions, inflexible monolithic systems, easy to break. They're starting to have software architectures emerge, but I don't think at current time there's an established standard of any kind. Also lots of interesting questions to ask from the research perspective. How do we actually reason about reflective systems? How do we prove them correct? What does it mean for a behavioral twin to be correct? We have programs interacting with knowledge. We have self-adaptation. We have model drift. We have problems of model synthesis. So there are lots of aspects that are interesting to analyze. I also am very interested, and I think it's a big topic, is data-driven formal methods. So how to generate verification problems on the fly from data. And this is a typical thing we will see here, where we have sensor data coming in, we have domain knowledge, and we want to synthesize models, but we would also like to synthesize verification problems. And I should mention, just to end, that I think the future is in having distributed digital twins, but actually how to do a small 2.0, which is more actor-based, so parallel and asynchronous, I don't know. I mean, the semantic lifting will have races with querying, so there might be issues there that will need to be resolved before one would know how to do semantic or self-aware distributed twins. So I will stop there. Thank you.
Thank you very much. It was a very interesting talk. Does anyone have any questions?
I have a couple of questions, if I may, Álvaro.
Yeah, go ahead.
Okay. Hi, Einar. Thank you very much for your lovely presentation. We are always talking about administration in FME. It's nice to hear about your scientific interests. Very, very nice talk. I had two questions, if I may. The first one is, I wonder if you'd elaborate a bit more on what you mean when you say that we now transforming a business managed problem into a software engineering problem. I don't believe you mean that we can now do away with business managers at all. So I wanted to understand better what you mean by that. And the second question is that I wanted to know how much, I think small you call your language, how much of it is specific to FMI? Is that a language to write FMUs? Does it embed the API of FMUs?
Okay, so I will start with the first one. I mean, I certainly don't think we will get rid of business management in the same way. I don't think we will get rid of lawyers either, for example. But what I wanted to point out is that there's enormous effort in facilitating by the means of digitalization how information from one stage in this construction can be carried over to the next stage. So this is really the point, is that the state of the art today is that you have these piles of documents, and they are partly forgotten as we move from constructor to operator, for example. And there's a huge effort in digitizing these things so that these are electronic artifacts that are interlinked, so that one can actually access information from other stages in these life cycles.
Okay, thank you.
So that's really what I meant. And then the second question is, so Small is embedding FMUs. It is not really made for programming FMUs. I think it's more like an orchestrator language for FMUs.
So you write master algorithms with Small?
You can do that, yeah. I mean, it is a programming language. It's not extremely expressive, but you can embed an FMU inside an object. So you can dynamically boot up objects which are embedding different simulators or different models.
So do you plan to replace FMI instead of using FMI? Are you telling, or is it an implementation of FMI?
It's just that's really just a small part of Small. So I mean, we have other embeddings, like we are embedding time series databases. I didn't mention it except in the example at the end. So this is really just because there are better languages to build these models than Small, and therefore it's interesting for us is to use models that exist and connect them together into the self-adaptive system perspective.
Okay.
I should also mention, just for the record, that we have an implementation of this semantic reflection for Java, for example. So it's not that it can only be done in this kind of small language. It's just that for us, it's convenient to work with Small because it is a formal language. It has a formal semantics, for example. So we can reason about it. While for Java, I don't think we can.
Okay. All right. Thank you.
Any other questions?
I actually had one of his, all right.
Yeah, go ahead, Ziggy.
Yeah.
Then there's one in the chat.
All right, sure. I'm interested about, so you mentioned the requirement monitor earlier. I have a question about this, but just first, is this implemented yet, or is this like an idea? Is this like a potential? And also, is this on the, like, I'm imagining it's like a runtime monitor on the managed system of the Mate K loop, right? And there were those two Mate K loops. So I was curious about more details about this, basically, about the requirement monitor. But yeah.
So a typical example, I mean, it is implemented first. So, but I mean, for us, the requirement is something that we are monitoring here. So I mean, in the mate loop, we have a monitor which is collecting information, and we are analyzing it with respect to a set of requirements. And this set of requirements is dynamic, so it will change. So, for example, this was the example I had with like a healthy plant versus a sick plant. So we want to treat them differently. So our goal in watering the plants will be different depending on the life cycle of the plant. So we have a dynamic swapping or changing of requirements in the same way as we have a dynamic changing of controllers.
That's very interesting. Sorry, I just had one last point about this, because why I was also asking is because, you know, there's this idea and discussion about what does correctness mean for when you're self-adapting. And in the RoboSapiens project I'm doing now, we have two notions. One that's like a trustworthiness checker, a runtime monitor, more based on the managed system, and then we have an idea of another of a legitimized component. Basically, the question is either checking the static requirements, or we're checking what the plan is, checking basically what the system's doing now, or checking what the plan is according to some other constraints. And I'm curious about the two directions that correctness for self-adaptation could go, and the two kind of ideas. I'm curious about that as well, and which one you're kind of, you know, moving more towards. And it sounds like it's more the runtime monitor right now, right, with the requirement monitor.
Well, I mean, the thing is that I'm interested in making twins of systems that we don't understand. So, for example, I'm working on a digital twin of the Oslo fjord and the biology in the fjord, and there's no way we can explain what's going on in the fjord in terms of transitions, for example. So there will be events that we observe that something has changed in the fjord, and we want to adapt our twin. So it's not that I'm against the other perspective. It's just that if we have complex systems, we will not be able to verify them. So that's the approach I'm taking here. But really the question is, what does it mean for a digital twin to be correct if part of what it's doing is to reconfigure the requirements that it is monitoring? And that's really the topic I was trying to discuss, is what does it mean that these kind of self-adaptive systems self-adapt correctly, so to speak?
Absolutely. Thank you. Very interesting.
We have a few questions in the chat. I'll read them just because of the recording. So one from David. It's a question about the greenhouse example. With a moisture sensor, we can tell if water is needed, given that we know the type of plant. We can look at the leaves to see how healthy the plant is, given that we know the type of plant, light, heat, etc. But I'm not clear on how the digital twin helps make the system better.
Well, it makes the gardener redundant. That's the basic goal of the digital twin here. But joking aside, the twin is really connecting a watering heater system to a knowledge graph, which determines like how should different plants be treated in different stages of their life cycle.
Okay, so the other question was from Peter. Do you do anything to take uncertainties, for example, from sensors into account? Do you consider the modeling of the physical elements, e.g. described with ODs or PDs?
Yeah. We have not done that so far. I think it's a good question. I think the uncertainties can be dealt with either in how sensor readings are integrated into the knowledge graph. So I think one would typically add some analysis component on the way before it is inserted into the knowledge graph. But I think also, and this is one thing we are thinking, is to start looking at having knowledge graphs describing like intervals, and we could even look at distributions for that matter. But we have not done so yet.
Okay, thank you. Any other questions?
If I may comment again, then I know the uncertainties actually matters a lot in terms of how sure you can be on the decisions you are making if you are trying to adapt to the things you are sensing, in a sense.
Yeah.
Particularly when you have a physical system that has a non-linear kind of behavior.
Yeah. Yeah, I agree. I mean, I don't have a good answer how to deal with the uncertainties. I mean, depending on to what extent you are doing control versus just shadowing, but one thing which one could also look at is portfolio, right? So you could have a set of models and you can start pruning them away as you learn more about the physical system, for example. So that's the kind of technique we have been exploring. For example, we have been doing things with pandemic prediction, and then we have been exploring how a pathogen spreads depending on different assumptions about reproduction of the pathogen and so on. But I agree that that uncertainties is really also a very interesting discussion here.
Any more questions, comments? Okay, I had one question, or kind of one and a half. So, given the bidirectional nature of the twins, could a inappropriate model cause the physical twin to reach a erroneous state or inefficient state? And if so, when you reconfigure the digital twin to correct some identified problem, could the digital twin kind of reset the physical twin to a better state?
I think that largely depends on the particular use case. But I mean, to link it more to what I was talking about. So if we have this knowledge graph and we have managed to represent kind of expert understanding of the physical system in that knowledge graph, then we could, and that's part of the idea, is that we can use that domain knowledge to try to avoid that or reduce the chances that this situation happens. So we want to link the configuration problem of the twin to the expert's understanding of the physical system to eliminate or to help eliminate bad configurations, so to speak.
Okay, thank you. Any more comments, questions?
So I have maybe a small question here. So Martin Achenbach from University of Lübeck. So so in your adaptation, you had a step where you're searching for a better model, basically. But given that there are different states in the system of the components, there could be a state explosion. It could be an intractable problem, search problem. So how are you handling this? Is there some like offline recompilation or some focusing technique also for large systems?
Yeah. We have not encountered that. I mean, I agree that it could be. We have not encountered it with the kind of systems we have been building so far. So we have been using these abduction techniques, but at least for the size systems we have been looking at, this has been working very well.
I see. Okay.
I don't know if you have a really large system, if you would want to try to structure it into sub-problems or something like that.
Some hierarchical structures.
Yeah, I could believe that one could do that kind of approach.
Okay, thanks.